Hello students, today we are going to discuss the convergence of the infinite series of the past two terms. This is our today topic. In this today contents is the objectives and introduction, convergence of the infinite series, theorems on series of the past two terms, and what is a summary, and one more concept is the introduction of alternating series test. Here today objectives are the distinguished among that is a notion of the convergence and absolutely convergence and conditional convergence of the infinite series that we want to be identify. Prove some theorems related to the convergence of the series with the past two terms, and another concept is comes to the it is a alternating series discussion we will discuss in this today's objectives. Now introduction part, it is a series. Series means is a sum of the sequence terms. It is a represented bracket of an is a sequence. It is a representation comes to the here summation n equal to 1 to infinite an. Here summation n equal to 1 to infinity an is a a1 plus a2 plus so on plus an, the sum of the terms up to infinite, so that it is a we can represent into the summation n equal to 1 to infinite an is called as the infinite series. That notation we can be represented bracket of an. Here we have examples of infinite series in the geometric progression is one of the infinite series example. Here geometric series is the a plus ar square plus so on, a r to the power of n minus 1 plus so on, because of infinite terms where r is less than 1. Here series of the terms, it is the summation n equal to 1 to infinite un, which is instead of summation n equal to 1 to infinite an, we are taking that is the sigma n equal to 1 to infinite un. It is a un is all the constants, even though this is also infinite series, and infinite series of the form summation n equal to 1 to infinite xn. That xn also we can be represented into the variable form. That variables are the it is n equal to 1 to infinite x1 plus x2 plus so on plus xn so on, so that it is also infinite series form. Now it is comes to the power series, because of it is a sigma n equal to 1 to infinite un into x to the power of n, where x belongs to R, the set of real numbers. This is called as the infinite series of the all the terms, so that it is a powers x to the power of n will be there, so that it is a instead of un is there, it is sigma un is there, it is a series, infinite series. Now into x to the power of n term if we use in this series terms have, then we can decide it is a power series. So the power series representation is a sigma n equal to 1 to infinite un into x to the power of n. Now that is a series representations for that is a it is a sum of the terms of the sequences, how it will be represented, that is overall idea about it today, introduction part. Now convergence of the infinite series, here sum of the sequence terms is represented as a series, that is a sigma n equal to 1 to infinite uk equal to u1 plus u2 plus so on plus un, that is called as a sequence of the partial sum of the infinite series. It is a sigma n equal to 1 to infinite un. If the Sn is tends to s as n tends to infinite, then it is a partial sum of the sequence, and as n tends to infinite it is clearly approaches to the some point or constant, then we can decide it is called as a convergent. Otherwise it is comes to the divergent. So a sigma n equal to 1 to infinity un equal to s, if the sequence Sn is a divergence, it is a sequence is convergent, because of it is approaches, partial sum is approaches to the s as Sn tends to s as n tends to infinite, so that directly we can decide it is clearly partial sum is Sn is equal to u1 plus u2 plus so on, un is as n tends to infinite we are approaching to the s, so that sigma n equal to 1 to infinity un is approaches to the s as Sn tends to infinite, so it is called as a convergent. And the divergence means it is a sequence is whenever it is not the finite, then we can decide into the divergent. This is a convergence of the infinite series. Now example if I take, it is a sigma n equal to 1 to infinite un equal to 1 plus 1 by 2 plus 1 by 2 square plus 1 by 2 cube plus so on 1 by 2 power n. What it is that it is clearly geometric series in the infinite series. Now it is a Sn I am taking here, it is a geometric series, so that directly it is a sum of n terms is we can represent Sn equal to a into 1 minus r to the power of n by 1 minus r, that is in the previous knowledge. In this formula it is a geometric progression. Here rth is a common ratio. If r lies between the minus 1 to 1, in this case it is a Sn equal to, here given series is a sigma un equal to 1 plus 1 by 2 plus 1 by 2 square plus 1 by 2 cube plus so on 1 by 2 power n plus so on. So here Sn equal to here a equal to 1 and r equal to 1 by 2, so that here 1 into a into 1 minus r to the power of n by 1 minus r, partial sum if we substitute, we get Sn equal to 1 into 1 minus 1 by 2 power n by 1 minus 1 by 2, that equal to 2 into 1 minus 1 by 2 power n. This is a partial sum of the n terms. So, if we multiply it 1 into 2 minus 1 by 2 power n minus 1. Now, if I apply that limit n tends to infinity Sn equal to, here only constant is a 2, 1 minus 1 by 2 power n minus 1, 2 power infinite minus 1 is a 2 power infinite, 1 by infinity is a 0. So, 2 minus 0 is a 2. So, that is a series is a already approaches to the some point S is a 2. So, that it is a series is convergence to 2. This is a geometric series we can check. Now, if I go for that is a consideration of another example, sigma n equal to 1 to infinity 1 by n into n plus 1. So, here limit n un equal to 1 by n into n plus 1 equal to 1 by n minus 1 by n plus 1 I can write. Here first term is comes to the u1 equal to 1 minus 1 by 2, u2 if I take 1 by 2 minus 1 by 3. Now, cancellation of the terms, I will get only the last sum, partial sum of the n terms is clearly 1 minus 1 by n plus 1 only, because of middle terms are the cancel, because of minus 1 by 2 plus 1 by 2 minus 1 by 3 plus 1 by 3 and so on. Here 1 by minus 1 by n plus 1 by n is the middle terms are the cancel. So, that it is a starting term 1 minus ending term 1 by n plus 1. Now, if I apply that is a limit n tends to infinity Sn, partial sum of the n terms as n tends to infinite, Sn tends to infinite, then n tends to infinite, we can get that finite value 1 minus 1 by infinite plus 1. So, 1 by infinite is a 0, 1 minus 0 is a 1. So, that it is a series is convergent, convergence to 1. This is another example. Now, it is a, if it is not a, for example, I am taking the uk equal to k, what happens k plus k plus k plus so on nk. Partial sum is a nk. If I apply that is a limit n tends to infinite, nk, n is a infinite, infinite into k equal to infinite only. Therefore, it is a not a finite partial sum of the sequence as n tends to infinite is not a finite. So, that it is clearly divergent to infinite. Now, here another example, sigma n equal to 1 to infinite 1 by n is not a convergent. Here through sequence of bracket of 1 by n is a convergence to 0. Now, here it is a, if we apply that, it is a existence of the subsequences of the series is not bounded. So, that it is a series is not a convergent. Now, how we can be explained? It is a Sk1 equal to 1 by 1 plus 1 by 2 and Sk2 equal to 1 by 1 plus 1 by 2 plus 1 by 3 plus 1 by 4, that we can write as a Sk1 plus 1 by 3 plus 1 by 4. Now, it is greater than 1 by 4 plus 1 by 4 Sk1 plus Sk1. So, that it is a 1 plus 1 by 2 plus 1 by 2, 1 by 2 it is a Sk2. So, that 1 plus 1 by 2 it is a answer is 2. Now, we go for that is a Sk3 is greater than 1 plus 3 by 2. So, on Skn is 1 plus r by 2. So, thus it means the subsequence of the terms are the not bounded. So, that it is unbounded, then it is clearly we can conclude that the series is a not a convergent, that is a series sigma n equal to 1 to infinite 1 by n. Next concept, it is the theorems on the series of the positive terms. Here I am taking the two series sigma n equal to 1 to infinity a n and sigma n equal to 1 to infinity b n. Be the two infinite series converges to L and M. First series is convergence to L and second series is convergence to M. Then and p comma q are any two numbers. If we take the coefficients, it is a product of the series. It is a sigma n equal to 1 example here, there we can see here sigma n equal to 1 to infinite p into a n plus q into b n. This is the term. Now, I want to apply that is a series at the time it is the convergence to the constant term will come to the common. So, into p and as sigma n equal to 1 to infinity a n is convergence to L. So, that p L and the second term will go for sigma n equal to 1 to infinite q b n. Q is a constant take common and sigma n equal to 1 to infinite b n as n tends to infinite and the limit is clearly m. So, that it is a second term is a q m. So, that it is a sigma n equal to 1 to infinite p a n plus q b n is convergence to p L plus q m. This is a overall theorem. Whenever we have a two series, it is a convergence to the L and m. Then it is a when we have a that is a coefficients, then that coefficients we can take the common and we can apply the limits. This is a overall idea about this first theorem. Now, I am going to prove point of view. I will take that is a LHS is a sigma n equal to 1 to infinite p a n plus q b n. Now, it is a Cn is a represented this Cn equal to sigma n equal to 1 to infinite p a n p a k plus q bk I am taking. Now, if I take that is a separation of the terms p into sigma k equal to 1 to infinity q ak plus q into sigma k equal to 1 to n bk. Now, it is clearly it is approaches to the p an plus q bn. Already an is a series is approaches to L and bn is a series is approaches to m. So that as n tends to infinity we can write as a cn is clearly approaches to the pl plus qm. So that it is as n tends to infinite. Therefore, the hence theorem is proved. Now, we can go further to the theorem 2 as sigma n equal to 1 to infinity an is a convergence, then an is tends to 0 as n tends to infinite. Now, it is clearly here an is approaches to the 0 as n tends to infinity. Directly we can decide it is clearly also the convergent. That is the second decision for this. So that it is a theorem 2. Now, in this proof point of view, I will take the one of the sequence series term is a bracket of Sn. It is denote that partial sum of the sequence of the given series. It is a Tn equal to Sn minus 1. That is one of the partial subsequence. Now, for that all n greater than 1, sum of the series is then Sn is tends to S as n tends to infinite. Then clearly Tn tends to S as n tends to infinite, since Tn equal to Sn minus 1. Now, I am going to take that is a in between the distance is a an equal to Sn minus 1. Now, it is a if I apply that is a limit n tends to infinity an equal to limit n tends to infinity Sn minus Tn. So that it is a separation of the terms, it is a limit n tends to infinity Sn minus limit n tends to infinity Tn. So, it is a first limit is a L and the second terms also, because of term means it is a Sn minus 1. So, partial sum of the n minus 1 terms also limit L and partial sum of the n terms also limit L. So, that it is a L minus L equal to 0. So, it is a nth term if we take that it is a an, that is a limit n tends to infinity an, it is a partial difference. Then we apply the limit also 0, then we can conclude that that series is clearly convergent. That is a hence theorem proved. Now, we go for the example 1. It is a sigma n equal to 1 to infinity n by n plus 1 is not a convergent. Because of I will apply that limit n tends to infinity an equal to limit n tends to infinity n by n plus 1 plus n plus 1, n we can take the common, numerator n and denominator n is cancelled. So that it is a limit n tends to infinite 1 by 1 plus 1 by n equal to, it is n tends to infinity 1 by infinity is a 0. So, 1 by 1 plus 0 equal to 1 is not equal to 0. Therefore, it is not a convergent. Directly we can conclude from the theorem 2. Now, theorem 3 is a Cauchy general principle of the convergence. So, sigma n equal to 1 to infinity an is a convergent if and only if each delta greater than 0 there exists a capital N such that for m is greater than n greater than or equal to n, as it is a mod an plus 1 plus an plus 2 so plus so on plus mod an mod term is less than delta. It is up to an terms, and after extension of n plus 1 n plus 2 so on up to an up to n terms, last term it is a the use mod value is less than delta, then we can say that it is a series is also convergent. This is another proof. Now, I will take the Sm and Sn are the two partial sum of the sequences, partial sum of the series and m terms and n terms, two terms of the series I am taking. Now, if I take the differences Sm and minus Sn, what we can get that it is a terms of it is more than an nth term. So, that it is n plus 1, so n plus 2 so on m term. So, that directly here Sm minus Sn when we will take there we get that is a Sn plus 1 an plus 1 plus an plus 2 plus so on plus am, that is a difference equal to Sm minus Sn. Now, it is a sigma n equal to 1 to infinity an is convergent if and only if it is a Sn bracket Sn is convergence. So, that it is a Cauchy general principle of the convergence of the sequence terms is a true, for this it is a convergent, hence it is a proof is also mod a n plus 1 plus a n plus 2 plus so on plus am is less than delta, then we can conclude sigma n equal to 1 to infinity an is a convergent, hence it is proved. Now, theorem 4 it is a Princism theorem is clearly it is explained that it is if the sequence of terms, it is a bracket of an is a series, in this series sequence terms it is a sequence of the positive terms and the series form is a sigma n equal to 1 to infinity an is clearly convergent, as n also tends to 0 as n tends to infinity. This is also one kind of theorem, because of it is a sigma n equal to 1 to infinity an is approaches to the 0 as n tends to infinity, it is a convergent. There we discussed in the previously theorem 2. Now, here also theorem 4 is also explained whenever it is in the decreasing sequence of that positive terms, then we can go for that is the sigma n equal to 1 to infinity an is convergent when it is a n into an is a tends to 0 as n tends to infinite. Now, it is a Cauchy principle, Cauchy principle of existence. There we can take that it is a every delta greater than 0, there exists a capital N such that it is a m plus 1 plus 1 plus a n equal to sigma k equal to m plus 1 to m a k is less than delta by 2. So that it is clearly n is greater than 2 n plus 1 because of n greater than m greater than or equal to n. Then it is n minus 1 by 2 greater than n, so that sigma a n is less than delta by 2. It is a summation of overall k we can get, so that n minus 1 by 2 is clearly less than k, less than or equal to n. So it is a k is greater than or equal to a n, the number of the terms is less than or equal to n plus 1 by 2. Thus it is a sigma a k is greater than or equal to n by 2 a n. Thus it is clearly as n a n also tends to 0 as n tends to infinite. Hence it is concluded that it is whenever the sequence is a decreasing sequence and positive term of the series is a sigma n equal to 1 to infinity a n is convergent as n tends to infinite a n, when it is a n a n is tends to 0. This is called as a Princism theorem. Now we can go for that is a one example. It is a n equal to 1 by n if n is greater n equal to 2 power k and 0 otherwise. Now it is a k is greater than or equal to 0 because of n equal to 2 power k. Now here, so I am taking that is a sequence term, it is s 2 k is a partial sum of the n terms. If I take it is a sigma n equal to 1 to 2 power k, a n equal to sigma j equal to 0 to k 1 by 2 power 0, 2 power j. So here 2 geometric series, so that 2 you take the common 1 minus 1 by 2 power k plus 1. So it is a 2 power k less than or equal to n less than or less than 2 power k plus 1. As it is a limit n tends to infinity s n, if you apply that, it is a, I will get that is a constant is a 2. Therefore, it is already it is a whenever it is a satisfy the theorem 1, then it is we conclude that sigma n equal to 1 to infinity a n is convergent. So it is n a is a does not tends to 0 as n tends to infinite whenever n a n equal to 1. So that case is come to the 0 otherwise. Whenever it is a k greater than or equal to 0, then we can say n equal to power k, then 1 by n is convergent, and whenever it is a 0, it appears whenever it is a as n a n equal to 1 as n tends to infinite. Next, it is a definition of absolutely convergent. Whenever that it is a sigma n equal to, it is an infinite series, sigma n equal to 1 to infinity a n is said to be absolutely convergent or convergence absolutely, both are same. If a series is a sigma n equal to 1 to infinity mod a n is convergent, then we can conclude it is clearly absolutely convergent. If it is not convergent, then it is not a absolutely convergent. So it is called as conditionally convergent, we can conclude. Now every absolutely convergent series is a convergent. That is a theorem number 5. Now I am going to prove that it is a sigma n equal to 1 to infinity a n is absolutely convergent. So sigma n equal to 1 to infinity mod a n is also convergent. Now I am going to check that it is every delta greater than 0, Cauchy general principle of convergence, for all there exists capital N such that directly we can take mod a n plus 1 plus mod here more than the terms here a m plus 1 plus mod m plus 2 so on plus so on, last term is a n mod is less than delta. Each term is less than delta, therefore it is a sum of all the terms is also less than delta. Therefore it is a theorem 2, directly we can conclude sigma n equal to 1 to infinity a n is a convergent by Cauchy principle. Now example, if I take that series sigma n equal to 1 to infinity minus 1 whole to the power of n minus 1 by n equal to 1 plus 1 minus 1 by 2 plus 1 by 3 minus 1 by 4. This is called as the alternating series. Alternating series is a not absolutely convergent. In this we can conclude that is a sigma k equal to some n plus 1 to infinite. So it is a into minus 1 whole to the power of k minus 1 by k. This is written in terms of 1 by n plus 1 minus 1 by n plus 2 plus 1 by n plus 3 minus 1 by n plus 1 plus so on plus minus 1 whole to the power of m minus n minus 1 by m. Now here if we go for the product form 1 by n plus 1 n plus 2, that is the first two terms, and his next two terms is a 1 by n plus 3 into n plus 4. After simplification of 1 by n plus 3 minus 1 by n plus 4 is a 1 by n plus 3 into n plus 4 plus so on, like that. It is a whenever the some terms is going on up to last, it is a less than term we can get, less than of 1 by n plus 1 into n plus 2 plus so on. Now if we go for the individual terms, it is a representation, and first term and middle terms will be the minus 1 by n plus 2 plus 1 by n plus 2 cancel. So middle terms all will be cancelled, and starting and ending term only we get. So 1 by n plus 1 is a starting minus 1 by n plus p plus 1 is a ending term plus 1 by m will be there. Now as it is a m minus n equal to 2p, if I take m minus n equal to 2p plus 1. so that it is a C, directly we can write as a less than 1 by n plus 1 plus 1 by n plus 1. Instead of 1 by n plus p plus 1, we can take 1 by n plus 1. So that it is a 2 by n plus 1, less than it is 2 by n. So it is concluded that sigma 1 by n power 1 by sigma 1 by n only. Therefore, already it is a sigma 1 by n is not a convergent. Therefore, it is series is clearly not a convergence. It is a hence it is clearly not a absolutely convergent. It means that conditional convergent. In the summarization, we can decide it is a infinite series summarization. It is in the 18th and 19th centuries. It is the discussions is happen that it is a convergence. It is in this explanation, adding the terms of the infinite sequences, it is comes to the series. Now, series is a partial sum of the sequence terms. If you apply the limit, then it is comes to the infinite series is a convergent. Whenever it is a sequence is approaches to as n tends to infinite, Sn is a tends to S, then it is series is convergent, and otherwise it is a divergent that we have discussed. Now, it is another concept is whenever it is one of the most useful results we discuss, it is the Cauchy principle of the convergence of the series and the primism theorem, and finally it is a difference between that is absolute and conditional convergent, and absolutely conditional convergence whenever it is not a convergence, it is a conditional convergence concepts we explained with the proofs, theorems. Now, another concept is comes to the introduction of the alternating series. In this introduction of alternating series, here objectives and introduction and alternating series concepts we are going to discuss here. Now, alternating series means it is a sequence, it is a bracket of xn of the non-zero real numbers is alternating if the terms is a minus 1 whole to the power of n into xn, or all are the positive or the all are the negative real numbers. It is some of the terms are the positive and some of the terms are the negative, then this sequence is called as the alternating sequence. Now, it is a series formation will come to the sigma n equal to 1 to infinite minus 1 whole to the power of n into some xn. This is comes to the alternating series because of terms are the some of them are the positive, some of them are the negative. Alternatively, it is a positive and negative, then we can decide it is a series is a alternating series. This alternating series terms is each term is we can be represented here given function. Now, here one example, if I take sigma n equal to 1 to infinite minus 1 whole to the power of n by n equal to minus 1 plus 1 by 2 minus 1 by 3 plus so on is a example of the alternating series. Now, alternating series test, it is a Leibniz test. The Leibniz test is clearly explained that it is a sigma n equal to 1 to infinite minus 1 whole to the power of n minus 1 into bn equal to, here first term is a positive b1, the second term is a negative minus b2 plus b3 minus b4 plus so on bn greater than 0 satisfies. Next, it is going for that, it is increasing terms, bn plus 1 is less than or equal to bn for all n, and limit n tends to infinite bn is equal to 0, then the series is clearly we can say that convergent. Next, this is called as a Leibniz test. Here Leibniz test, whenever it is alternating series test, directly we use that it is a particularly here nth term we will take and apply the limit n tends to infinite, it is a term is equal to 0, then series is clearly we can say that convergent. Now, example 1, it is if I take on this, it is alternating series. Here above test is clearly called as a Leibniz test, that is alternating series test is called as a Leibniz test. Leibniz test, it is a alternating terms, it is nth term if I take limit n tends to infinite bn equal to 0, then series is clearly we can say that convergent. Test for convergence of the series, sigma n equal to 1 to infinite minus 1 whole to the power of n into 1 by n. Now, here bn equal to how much? 1 by n. So, as n tends to infinite, limit n tends to infinite 1 by n equal to 1 by infinite equal to 0. So, it is a 0 and alternating series because of minus 1 whole to the power of n, sigma of minus 1 whole to the power of n into 1 by n. So, we can say limit n tends to infinite 1 by n is equal to 0, therefore, it is a series is convergent. Next, it is example 2. Test the following the series of the convergence, sigma n equal to 1 to infinite minus 1 whole to the power of n into n by n square plus 1. Here, I will take it is the nth term is a n by n square plus 1. Now, it is a limit n tends to infinite n by n square plus 1 equal to limit n tends to infinite 1 by 1 plus n square, because of I will take the n square is a common in the denominator. If I take n square into 1 plus 1 by n square, in the numerator here n cancel, 1 by n will be there, that I will take into the numerator. So, limit n tends to infinity 1 by n by 1 plus 1 by n square, 1 by infinity is a 0 divided by 1 plus 1 by infinite square is the 1 by infinite square is also 0. So, 0 by 1 plus 0 equal to 0, therefore, it is a series is convergent. Now we go for the example 3. Test the series for the convergence. It is a sigma n equal to 1 to infinite minus 1 whole to the power of n into 2 n square by n square plus 1. If I take that, it is a something, it is a sigma n equal to 1 to infinite minus 1 whole to the power of n into bn. So here bn equal to what is a 2 n square by n square plus 1. Now it is a n square, you take the common in the numerator and the denominator, both n square numerator denominator are the cancelled. So rest of the terms are the 2 by 1 plus 1 by n square. Now I will apply the, this is a bn. So limit n tends to infinite, here 2 by 1 plus 1 by n square, this is a 1 by 1 square n square, limit apply, it is a 1 by infinite square, 1 by infinite square is 0, 2 by 1 plus 0 equal to 2. It is clearly not the 0, so that it is clearly series is a divergent. Already series is clearly divergent because of it is a Leibniz test fail. Now example 4, if I test the following the series for the convergence, sigma n equal to 1 to infinite minus 1 whole to the power of n into cos pi by n. Now bn equal to cos of pi by n, it is a bn is greater than 0 for n is greater than or equal to 2. Now if I apply the limit n tends to infinite cos of pi by n equal to limit x tends to infinite cos of pi by x, that is equal to pi by infinite 0, cos 0 is 1, not equal to 0, therefore series is a divergent. So directly we can conclude that it is a sigma n equal to 1 to infinite minus 1 whole to the power of n cos pi by n is clearly divergent. Now it is a absolutely convergent or conditionally convergent. Now definition, sigma n equal to 1 to infinite minus 1 whole to the power of n minus 1 a n is a convergent series. Then it is a Leibniz test, it is a convergent alternative series, and sigma n equal to 1 to infinite mod a n is divergent by using the other test. So it is a divergent and it is a convergent. Alternative series is a convergent by Leibniz test, previously I explained. Now it is a series is a mod, if I apply it is a divergent, then it is a series is alternative series is conditionally convergent. When that it is a sigma n equal to 1 to infinite minus 1 whole to the power of n minus 1 a n is a convergent series, and sigma n equal to 1 to infinite mod a n is a convergent, both are the convergent, then we can say it is absolutely convergent. Now example, if I take, it is a minus 1 whole to the power of n plus 1 into 4n by n, 4n to the power of 6 plus 5, it is a sigma n equal to 1 to infinite. It is clearly bn is a, if I take 4n by 4n to the power of 6 plus 5. Now it is a n is cancelled, so that if I take the common 1 by n to the power of 6, so that 1 by infinite is a 0, therefore it is a convergent observed by Leibniz test. Now if I apply the mod, it is a mod is a clearly 4n by 4n to the power of 6 plus 5. Now I apply that is a D'Alembert ratio test. If I apply it is a tends to 1, therefore it is a test is clearly we can say that convergent. So that it is a both are the convergent, therefore it is called as a absolutely convergent. In this total summarization, it is we discussed that it is infinite series is convergences and divergences, absolutely convergent and absolutely conditionally convergent, and infinite series various theorems we discussed in this session.